the last item that we have in this section is verifying the normality requirement in a one-way ANOVA. One requirement that must be satisfied to conduct a one-way ANOVA is that the K populations must be normally distributed. We verified this requirement in the calcium consumption example by drawing QQ plots in place of normal probability plots for each of the K equals 3 samples to see if the plots suggested that the data could come from a population that's normally distributed. A potential problem with this approach is that if the sample sizes are small, then drawing normal probability plots for each sample does not shed enough light on whether the normality requirement is satisfied. So for example, if I pull back in our previous example of the calcium consumption problems for children who consume lean meats, mixed meats, or higher fat meats exclusively. So in this particular case, we had sample sizes of 8 for each of the 3 groups. And again, to verify the normality requirement, we did a QQ plot for lean meats, we did a QQ plot for mixed meats, and we did a QQ plot for higher fat meats to show that each one of those probably came from a normal distribution. But again, a potential problem with this approach is that if the sample sizes are small, and a sample size of 8 is pretty small, then drawing normal probability plots for each sample does not shed enough light on whether the normality requirement is satisfied. So to address this issue, it's possible that even though the 3 individual QQ plots indicated that we have a normal population for each of the groups, because we have small sample sizes, that could still be problematic. To address this, we can verify the normality requirement by using a normal probability plot or a QQ plot of the residuals of differences between each data value and the sample mean for its level of treatment. So for example, verify the normality requirement for the calcium consumption data from the previous examples that we've done. So what I have here is a table where I have calculated the individual residuals for each data value. So I've organized this in a table here. And so I just want to, again, kind of go through and explain what I've done here. So for the lean meats, first of all, the first 8 data values here, so from here to here, that's the lean meats data. And these 8 values right here are just the values here from the lean meats data. This is the calcium consumption for the children who consume only lean meats. So it's just a repetition of this. And then here, I have the mixed meats data. So you can see the 897.7 through the 920.2. So again, this is the calcium consumption for the mixed meats children. And then I have for here, I have the higher fats meat calcium consumption. And again, that's just a duplicate of these data values. Well, what I have here in this next column, this is the mean of all of the lean meats data. So if I take these 8 data values here for lean meats and I find the mean of those, that mean is 794.7625. And likewise for the mixed meat, if I take the 8 mixed meats data values and find the mean, that mean is 898.5375. So I've just written that down here. And then likewise, if I take the 8 higher fat meats data and find their mean, that mean is 829.2375. So I've just rewritten that 8 times here. So to find the residual, I'm going to take each data value minus the corresponding mean. So if I take 844.2 minus the mean for lean meats, which is 794.7625, that gives me the residual, which is 49.4375. And if I do the same thing here, 745.0 minus the 794.7625, that is negative 49.7625, and so on. Now, when I get to the mixed meats, I'm going to take the data value minus the mixed meats mean. And so 897.7 minus 898.5375 gives me a residual of negative 0.8375. And likewise, when I get to the higher fat meats, I'm going to subtract the mean for the higher fat meats. So what I have here in the far right column is the residuals. So again, the residual here is defined as the difference between the data value and the mean for the treatment. And so that's what I've labeled here. This is the sample mean of the treatment. And so if the treatment is lean meats, then that's the sample mean of the lean meats. If the treatment is mixed meats, then that's the sample mean of the mixed meats, and so on. So I have these residuals, and so to verify the normality requirement, I can do a normal probability plot or a QQ plot of these 24 residuals. So if I bring up StatCrunch, so here I have this same table of information in StatCrunch. So again, I have the level of treatment, so either the lean meat, the mixed meat, or the higher fat meat. I have the data values, the calcium consumption. I have the 3 different sample means for the particular treatments listed. And then I've calculated the residuals here. So I have the 24 residuals, and that's what I'm going to do a QQ plot of. So I'm going to go to Graph, and I'm going to go to QQ plot. I'm going to select residuals because that's what I want to do a QQ plot of. I'm going to have it calculate the correlation statistic, and I'm going to put the normal quantiles on the y-axis and say compute. When I do that, I get this QQ plot. Now, the correlation statistic is 0.975. And by the way, notice, I mean, that's not super linear looking, but if you draw that line through there, that does look somewhat linear. And again, we do have a correlation statistic of 0.975. So I'm going to write that down, R equals 0.975. And now I'm going to come back to my notes. So the correlation statistic for the QQ plot for these 24 residuals is 0.975. Now, if I compare that to the critical value, if I have 24 data values, the critical value is 0.957. So our critical value for this plot is 0.957. And so because our correlation statistic 0.975 is larger than the critical value 0.957, then this verifies the normal requirement. So the residuals come from a normal population. So the residuals are normal, and again, we can use that to verify our normality requirement to be able to do an ANOVA test.